شباب, let's continue today. Last time we talked about how to write down the combustion equation for different kind of fuel, how to calculate actually the fuel to air ratio, actual air to fuel ratio in case when we have an excess air or something. And we have defined actually the excess air factor lambda, which is the ratio between the air to fuel ratio actual divided by the theoretical air to fuel ratio. And we defined also the parameter, which is the equivalence ratio, which is just one of lambda. But usually, the equivalence ratio is the most frequent actually parameter that is used. Actually, it is frequently used actually in combustion instead of as a parameter lambda. But just actually both of them are just to give us indication about the amount of excess air for the combustion process. So we have learned last time how to write down the combustion equation for a given excess air amount and how to calculate actually the air to fuel ratio. We have considered last time, Shabab, in case when we have a single hydrocarbon fuel, let's say 1 kilomole of fuel, 1 CmHn, like let's say octane fuel, how to write down the combustion equation and how we can calculate actually all the combustion product. This شباب, we assume we have complete combustion. We assume N2 is an inert gas, so we don't have any intermediate reaction or kinetics. However, actually we have a lot of kinetics. We don't have actually just a transfer from isooctane plus oxygen. It will just give us H2O and O2 and N2. This is a case that is actually highly simplified. Even the reaction of methane CH4 with oxygen, it contains actually about more than 100 steps. And this is for the simple mechanism actually for the reaction of CH4. But here we just have an indication, general indication about actually the combustion equation and the fuel stoichiometry in this case. We learned last time how to write down this equation if we have single fuel. We have considered some example. And we said also if we have mixture of two hydrocarbon, I gave an example last time. If we have two hydrocarbon of ratio 1:1 by volume, that means if we have 1 kilomole of the fuel, usually we write down the equation per 1 kilomole of the fuel. If it is the ratio 1:1, that is mean it is 50-50. So it will be 0.5 kilomole of the first fuel plus 0.5 kilomole of the second fuel. So we can write it if we have more than two, Shabab. Let's say we have 3 hydrocarbon fuel with those concentration here, 15%, 20%, 65%. So whatever the number of hydrocarbon fuel, I will assume 1 kilomole of the fuel. So in this case, if we have 1 kilomole, then we can divide actually all of this number by 100. Then the first actually hydrocarbon fuel, CM1HN1, will have actually 0.15 kilomole. If we have 1 kilomole of the total fuel, plus 0.2 from the second hydrocarbon, plus 0.65 actually from the third hydrocarbon fuel. And then I will write down the equation the same way, plus lambda gamma O2 plus 3.76 N2. That should give us MCO2 plus N over 2H2O plus lambda minus 1 gamma O2 plus lambda gamma 3.76 N2. But in this case, the value of M, Shabab, M, if we have single hydrocarbon, M is the number actually of carbon atoms, and N is the number of hydrogen atom in the fuel. If we have mixture of hydrocarbon like this, so M in this case will equal to 0.15 M1 plus 0.2 M2 plus 0.65 M3, and this is the M. And N, like this, we can calculate N, and the gamma is equal to M plus N over 4, which is the theoretical amount of air required actually in order to convert this fuel from the reactant. We can convert it actually to the combustion product. And the air to fuel ratio, it will be the same way. This is the air. Number of moles is lambda by gamma multiplied by the molecular weight of O2, which is 32, plus 3.76 multiplied by the molecular weight of N2, which is 28. This is divided actually by the mass of the fuel. We have 1 kilomole of the fuel in this case. So it will be equal to M, the number of carbon atoms, multiplied actually by the molecular weight of carbon, plus N multiplied by 1 in this case. This is in case, Shabab, if we have يعني a mixture of hydrocarbon and the concentration are given in volumetric concentration. So usually شباب when we write down the combustion equation we write it per kilomole. We need the number of mole, we don't need the mass. طيب if I give you the concentration يا شباب of those hydrocarbon fuel by mass, so how we can proceed in this case? Do you have an idea? So the Mohsen?
Divided by molar mass.
By the molecular weight you mean?
Yes.
So this is one option, شباب. If the concentration, you have either two options. This is actually if the mass concentration are given. We have an equation based on which actually we can convert actually from mass fraction to mole fraction. We have already considered this equation. This is actually the form. This is the equation by which we can convert if the mass fraction are given. We can actually convert it actually to the mole fraction, and then we can come back here to the same equation and assume actually 1 kilomole of the fuel, and then I will be solving in this case this way. But this will be time consuming in this case. If the mass fraction are given, I will assume actually instead of 1 kilomole, I will assume actually we have 1 kilogram of the fuel. So if we have 1 kilogram of the fuel and we have 15% of the first hydrocarbon, that means we have 0.15 kilogram of the first hydrocarbon plus 0.2 kilogram from the second, and the remaining for the third one. And in this case, شباب, we have to divide, as Abdul Mohsen said, we have to divide actually by the molecular weight for each component. Then we can calculate the number of moles for each fuel. So I will calculate here the number of moles actually for the first hydrocarbon, number of moles for the second hydrocarbon, and the number of moles for the third hydrocarbon. And the number of moles, شباب, will equal to the mass divided by the molecular weight for each hydrocarbon in this case. And then I will be writing the equation the same way. Plus lambda gamma O2 for the air plus 3.76 N2. That should give us the same MCO2. Same. It will be typically the same equation, but actually those number will be different. 0.2 instead of 0.15, 0.2, 0.65. If it is by mass, I have to divide this value by the molecular weight for each fuel. Okay. And the same way I'll be calculating Mn, then I can calculate gamma, and this will be the air to fuel ratio. But the air to fuel ratio by mass, شباب, in this equation, do I need actually to multiply the number of mole by the molecular weight to get for each fuel and sum them up to get the total mass of the fuel? Do we need that? So if the mole fraction are given, so just to calculate the mass of air, I just calculate it is actually the number of moles for the hydrocarbon for the carbon atom multiplied by the molecular weight M multiplied by 12 plus N multiplied by 1. But if the mass fraction are given, we assumed from the beginning actually that we have 1 kilogram of the fuel. So the equation that I have written is per 1 kilogram of the fuel. So the air to fuel ratio by mass will equal to the mass of air, lambda gamma multiplied by the molecular weight of air, divided by 1 in this case. I will be solving an example to show this. طيب, the third stage, if we have alcohol fuel, if we have alcohol fuel is just hydrocarbon fuel, but it is oxygenated fuel. So we have some oxygen actually in the structure of the fuel in this case. So when we write down the combustion equation, it will be the same way, plus lambda gamma of the air, that should give us MCO2 plus N over 2H2O, plus the same way, lambda minus 1 gamma O2 plus lambda gamma 3.76 N2. But in this case, the gamma or the stoichiometric coefficient or the stoichiometric number of moles of air will equal to M, number of carbon atoms, plus N over 4. But we have to subtract actually the amount of oxygen contained in the fuel. We have to add actually minus Z over 2. Here is an example, شباب, if we have ethanol, C2H5OH. We can just rearrange it to be in the form CmHnOZ. So it will be C2, we have H5 and we have H here, so it will be C2H6 and we have O in this case. So in this case, شباب, for this fuel, M is equal to what? C2H6O. M is equal to what, شباب? M is equal to number of carbon atoms is equal to 2, number of hydrogen atom is equal to 6, number of oxygen atom in this case is equal to is equal to 1 in this case, and gamma will equal to m plus n over 4 minus z over 2. That should equal to 3. And we just write down the air to fuel ratio to equal to here شباب we have stoichiometric. He said we need to calculate the theoretical air to fuel ratio. When I see theoretical شباب or stoichiometric, that means actually lambda is equal to 1 in this case. So we have theoretical combustion. If lambda is equal to 1, that means actually we don't have O2 in the exhaust gases. If lambda شباب equal to 1 or less than 1, that means we don't have enough air. So in case of lambda is equal to 1 or less than 1, we don't have O2 in the exhaust gases or in the product. So in this case, air to fuel theoretical will equal to gamma multiplied by 32 plus 3.76, 28 divided by the mass of the fuel. Mass of the fuel in this case, شباب, will equal to what? So Mustafa, mass of the fuel in this case will equal to what?
Mass of the fuel, we multiply the m by 12.
So air to fuel ratio شباب in this case will equal to what? The mass of air divided by the mass of fuel in this case. And the mass of air is equal to gamma for theoretical combustion, 32 plus 3.76 multiplied by 28. But for this fuel, we have actually C2H6O. This is actually the fuel. And we write down the equation per 1 kilomole of this fuel. So in this case, the mass actually of the fuel will equal to 1 multiplied by C2, so 2 multiplied by 12, plus H6, so 6 multiplied by 1. Don't forget we have O, 1 O, so this is actually 1 multiplied by 16 in this case. And this is شباب the air to fuel ratio. We call it theoretical, or we call it شباب stoichiometric. So when we say theoretical or stoichiometric, that means in this case شباب that lambda is equal to 1 in this case. So we have lambda gamma multiplied by O2 plus 3.76 N2, and that should give us the regular combustion product in this case. When we say stoichiometric or theoretical, that means the excess air factor lambda is equal to 1. طيب, this is شباب the case when we have alcohol fuel. Here is an example. Let's solve this example. He said we have a blend of liquid octane. So in some cases, شباب, I think we have went actually through the fuel structure, and from the name of the fuel, you should be able actually to predict its chemical structure. So I may not give you actually. I will say we have liquid octane or octane. You have to know actually that octane is C8H18. Yes, Hassan, go ahead.
يس دكتور صورتك مو واضحة دكتور تقطع.
Sorry?
الصورة عندك تقطع دكتور ما نشوف واضح.
شباب, is it the same for all?
Same for me.
Yes.
Yes,
Yes, me too.
So this is I don't know. This is KFUBM internet. I don't know. طب شباب, I will just end the call and then I will get back again. Is that okay?
Okay.
So it will be يا شباب technically I will just contact the ICTC. طيب here يا شباب the solution here that is on the slide is just a little bit different from what I am doing يعني. Hopefully it will be. I don't know شباب, can you join Zoom or something in the next time? We can make it through Zoom, or I don't know if it will be better.
If you give us the link, we will.
Sorry?
You give us the link for the Zoom, we will go there.
Yeah, so inshallah, so we can make it from next time يعني. But in this case, شباب, the solution here is given on the slide is a little bit different from the one I am presenting here. So just you can follow by voice. So in this case, شباب, M will equal to what for a mixture of hydrocarbon? M will equal to 0.9 multiplied by the number of moles for the octane, which is 8, plus 0.1 multiplied by the number of carbon atoms actually in the other fuel, which is ethanol, which is actually 2 in this case. This is M. The number of hydrogen atoms will equal to 0.9 multiplied by 18 plus 0.1 multiplied by 6 in this case. But don't forget يا شباب that we have in this case alcohol fuel. We have oxygen. So in this case we have to calculate Z. Z will equal to 0.1 multiplied by the number of oxygen atom which is 1. So actually Z in this case will equal to 0.1. And the gamma, which we need in the equation, will equal to M plus N over 4 minus Z over 2. M in this case, we can just calculate this value. It will be actually 0.9 multiplied by 8 plus 0.1 multiplied by 2. And we have calculated N and we have Z. If we calculated actually M plus N over 4 minus Z over 2, if you calculate all of that, it should equal to 11.5. So gamma is equal to 11.5 in this case. And based on that, شباب, we can calculate the air to fuel ratio, which will equal to gamma here on the slide, the lowest actually part. The air to fuel ratio by mass will equal to gamma multiplied by 32 plus 3.76 multiplied by 28 divided by the mass of fuel. But mass of fuel in this case, شباب, should equal to what? The number of moles. Exactly, 0.9 multiplied by the molecular weight of this fuel, which is 12 by 8 plus 18 by 1 plus 0.1 multiplied by the other fuel. And don't forget, شباب, that we have O, and there is a common error that you consider O as O2. O has the molecular weight 16, O2 actually has the molecular weight 32. So here we have one O in this fuel, so it will be actually 1 multiplied by 16 in this case. Then we can calculate the air to fuel ratio. Is that clear, شباب? Is it clear?
Yes.
Let's follow شباب here and see actually this is the third case if we have mixture of hydrocarbon. We have considered the case when we have single hydrocarbon fuel, CmHn. We have considered the case when we have a mixture of hydrocarbon fuel with different concentration, how to write down the combustion equation. And also the third case when we have alcohol fuel, we have some oxygen. In this case also we have learned how to write down the combustion equation and calculate the air to fuel ratio. But there are some grades of fuel, شباب, which have multiple components, like natural gas. Natural gas is mainly methane. Most probably it is methane, but we have some other impurities. And also in case of coal, when we have coal, the fuel actually have many components, including you may have actually a fuel containing CH4, carbon dioxide, and in this case we may have sulfur, carbon monoxide, oxygen, hydrogen, radical. You will find everything inside this fuel. In this case, شباب, if we have a fuel with this various concentration of different components, how we can write down the combustion equation, how we can calculate the air to fuel ratio in this case, or how we can calculate the amount of air required actually to burn this fuel fully and convert it into combustion product. If you look here, شباب, so it will be just simple. If we have the volumetric concentration of the fuel, so it will be the same way as we do. I will assume actually 1 kilomole of the fuel. But be careful, شباب. If we assume 1 kilomole, this is actually the percentage out of 100. So when I assume 1 kilomole, I have to divide each number here by 100. Okay? So let's say here we have 0.1. So don't do actually this error and write down in the equation, in the combustion equation, actually that we have 0.1 S. No, it has to be 0.1 divided by 100. So it will be 0.001 of the sulfur in this case. Usually the sulfur in the fuel should be actually at the lowest level, should be actually at very low concentration. Okay, so when we assume 1 kilomole of the fuel, those are actually the percentages out of 100. So we have to divide all the components by 100. So we'll have, if we have 1 kilomole of this fuel, we should have 0.1 CH4 plus in this case 0.2 CO2 plus 0.1 divided by 100 S plus 0.3 N2 and so on. This is actually our fuel. And I will write down the combustion equation. I will just write it general plus the air. It will be lambda plus gamma. Air is O2 plus 3.76 N2. This is the air. And that should give us the combustion product in this case. What kind of combustion product we should have in this case, يا شباب? We should have what? We have methane. We have hydrocarbon fuel. Hydrocarbon, carbon plus hydrogen. Then we should have carbon dioxide plus water. But I don't know the amount of this carbon dioxide plus water. Because actually we don't have the number of moles M for the fuel. We have actually different component, as you can see. So I will assume in general we have a number of atoms or alpha number of atoms of carbon dioxide plus B or beta number of carbon atoms of water vapor. In this case also plus, for a given lambda, شباب, we should have actually lambda minus 1 gamma O2. This is actually typically we should have. N2 coming in is the same as N2 leaving, but the fuel itself has some N2. So we have 0.3 N2 plus lambda by gamma 3.76 N2. So this is actually the N2. Plus we have sulfur in this case. Sulfur is burning with oxygen to convert to actually to sulfur dioxide. So I will say here plus C multiplied by the sulfur dioxide in this case. So if we have carbon, it should convert to carbon dioxide. Having a hydrogen, it should convert actually to water vapor in this case. O2 and the N2, we should have lambda minus 1 gamma O2, and the N2 coming in is the same as leaving. But do we have any other fuel, any other component that can be converted, that can react? We have here carbon monoxide. Carbon monoxide need oxygen, and it will be converted to carbon dioxide. Any carbon will be converted to carbon dioxide, but we have sulfur here. Sulfur will be converted to sulfur dioxide in this case. So we are left in this equation, if lambda is given, for this combustion, the excess air factor is given, then in this equation, we are left actually with 4 unknown. We have the value of gamma, value of constant A, value of B, and value of C. Then in this case, actually, we can just apply balance for carbon and the hydrogen, oxygen atom, and also for the sulfur. Then we can get actually all of these constant. And then we can calculate the air to fuel ratio regular way. It should equal to lambda by gamma multiplied by the molecular weight divided by the mass of fuel. Mass of fuel, this is the fuel starting from this point, 0.1 CH4, and ending at 0.3 N2. All of this is considered as fuel. Okay? So the mass of fuel will equal to the summation of number of moles multiplied by the molecular weight. It will be 0.1 multiplied by the molecular weight of CH4, which is 16, plus 0.2 multiplied by the molecular weight of hydrogen, which is 2, and so on, until we reach the final component of the fuel, which is N2. We have 0.3 here, N2. We have 0.098 O, so it will be 0.098 multiplied by 16. So the all fuel component, ya shabab, we have to consider the number of moles multiplied by the molecular weight, then we can calculate the mass of the fuel. Type if this is actually the volumetric concentration, ya shabab. If the mass concentration are given, so it will be the same as we said. I will assume 1 kilogram of the fuel, and in this case I will divide this number, which is the number of mole. It should be the mass in this case. I will divide it by the molecular weight for each fuel, and I will calculate actually the number of moles of each fuel. Then we can calculate the air to fuel ratio, but the mass of fuel in this case should be 1. Let's see an example like this case if we have the concentration are given on mass basis. So let's consider here a fuel. We have a certain cool fuel with the following concentration. We have 82% carbon, and we have 5% H2O, 20% hydrogen, and we have 1% oxygen, plus actually 10% ash. Ash is the salty component, salty solid component in the fuel. So this is actually, it is not actually an element. It is just as a salty component. It does not come into the reaction. We don't include it actually in the combustion equation. Those are the mass basis concentration, and we need to determine actually the air to fuel ratio if we have excess air equal to 50%. What does it mean? We do have 50% excess air, shabab. If we have 50% excess air, lambda is equal to what?
0.5.
1.5.
Exactly. So lambda in this case should equal to 1.5. And in this case, if the mass basis, the mass concentration are given. We need to write down the equation يا شباب in terms of the number of moles. We cannot write down the equation in terms of the mass. We have to have the number of moles. So I will assume in this case that I have 1 kilogram of this fuel. So 1 kilogram, that means I have to divide this number by 100. That means we have 0.82 kilogram of carbon. So this should be the mass of carbon. And that we have 5% H2O divided by 100. So 0.05 mass of H2O plus 0.02 from H2 plus 0.01 from the O2. This should be actually the mass for each element. Then we have the molecular weight of carbon. This is 12, H2O is 18, H2 is 2, O2 is 32. So we just list them. Then we can calculate the number of mole for each actually component of the fuel will equal to the mass divided by the molecular weight. Then we can calculate this is the number of mole for each fuel. Just to go back here and write down the combustion equation. So it will be this number of moles of carbon. Here it is 0.0683 of carbon plus 0.0028 of H2O and so on for hydrogen and for oxygen in this case. And I will write down the equation the regular way, plus lambda, which is 1.5, multiplied by gamma. I don't know in this case the value of gamma. I have to make balance in order to calculate O2 plus 3.76 N2. And that should give us, I will assume we have XCO2 plus Y H2O plus lambda minus 1 gamma. Lambda is equal to what, شباب?
1.5.
1.5 minus 1 should will be 0.5 multiplied by gamma. This is O2 plus lambda gamma 3.76 N2. Then we can make carbon balance. We can carbon balance. It will be 0.0683. This is the number of moles of the reactant of the carbon in the reactant side. That should equal to XCO2. That means we have X carbon atom in the product. So in this case, X should equal to 0.0683. That should be the value of X. Like this, we can make hydrogen balance. We can calculate the number of moles of Y, which is the number of moles of water in the product. And also we can make O2 balance. Then we can, in this case, calculate the value of gamma in this case. Okay. In order to double check, شباب, can we do something else? Because you may have some error in calculating X, Y, or gamma. So can we double check with something else? Double check those values. Do we have any other element to balance?
Maybe the mass balance.
We can make balance for what, شباب?
For nitrogen.
For nitrogen, exactly. So in this case, I can make one more balance for nitrogen. So I can get another relation actually for gamma. And in this case, actually, I will double check the value of gamma that I have calculated earlier from the balance of O2. Okay, so you can just make this double check in order to make sure that your solution is just correct. Then we can calculate the air to fuel ratio. We assumed 1 kilogram of the fuel, and based on which we have calculated the number of moles of each component. So the mass of fuel is equal to 1. Mass of air should equal to gamma, lambda multiplied by gamma multiplied by 32 plus 3.76 multiplied by 20 multiplied by 28 in this case. And based on that, شباب, we can calculate actually the air to fuel ratio, by mass. Okay, is that clear, شباب? Is it clear, يعني, or there is any kind of difficulty or something?
Yeah, clear.
So, يعني, it's straightforward, شباب. It's interesting. So let's move to the last case, how to write down the combustion equation. But in this case, we don't have the fuel. In this case, we have the product analysis of the combustion gases. Like in the tail section, in the tailpipe of your car, in the exhaust pipe, we can measure the concentration actually of the exhaust gases. Usually, شباب, even if the combustion is complete, usually you will find in the concentration of the exhaust gases, you will find some CO. Usually it is coming from the dissociation of the created carbon dioxide due to the high temperature. It can be dissociated back to carbon monoxide plus oxygen. So usually in the combustion product, you will find some CO, you may have some hydrogen, you may have some unburned hydrocarbon, some oxygen. Even actually, if we have less air, lambda is less than 1, you may have some oxygen as well, because we don't guarantee actually that the fuel will be mixing perfectly actually with the air inside. So in the product, you may have actually different kind actually of concentration. But actually, if we have the combustion product analysis, based on this analysis, Shabab, we can know actually the amount of fuel coming in, and we can calculate the air to fuel ratio, and we can calculate the excess air factor also. And this is a Shabab, a technique used also to control the emission in internal combustion engine. Usually we have in the exhaust section, we have what's called actually the Lambda Sensor. This Lambda Sensor, Shabab, measure actually the concentration of the product, mainly oxygen, and based on that actually it calculates the actual air to fuel ratio inside the engine, and it calculates the amount of excess air. Then it provides actually the electronic control unit with this signal so that actually it can control actually the flow rate of air and the flow rate of fuel, so that actually we can reduce the combustion emission. So there is in your car, and most of the modern car, we have the Lambda Sensor. Lambda Sensor measures the concentration of oxygen in the exhaust, so that actually it can have indication about the air to fuel ratio. Then it can modify this air to fuel ratio in order to reduce the combustion emission in this case. So if we have unburned hydrocarbon in the combustion product, that means we have fuel, more fuel in the combustion product. That means we have to reduce the amount of fuel injected, so that we can reduce actually the emission of hydrocarbon fuel in this case. Okay, so this is the function of the Lambda Sensor. To measure the concentration of the exhaust gases, we have the gas analyzer. And usually actually the gas analyzer actually provides the concentration on volumetric dry basis. Okay, so usually it gives the concentration in percentage, in volumetric concentration, or it can be given in part per million. We have 1 part per million is equal to 10 to the power minus 4 the volumetric concentration. So if I give you the concentration in a problem or something, let's say in part per million, you can convert it actually to the volumetric concentration, and then you can write down the combustion equation as we will proceed inshallah right now. Okay, so it is measured either in volumetric concentration, or the gas analyzer measure it actually either in volumetric concentration or in part per million, or it can be measured in some cases in milligram per meter cube. And this is actually the unit of measuring the concentration of the exhaust gases. But usually, there are two techniques to measure the concentration of the exhaust gases, either based on the dry analysis. Dry analysis means we don't have H2O in the product. Wet analysis, that means we do the analysis of the product to know actually the concentration of each species, including the water vapor. Usually, Shabab, the water vapor, it can affect actually the accuracy of calculating the concentration for some other gases, especially carbon dioxide. So there is a technique in order to measure correctly the concentration of the exhaust gases. Just we cool down the exhaust gases, then water vapor will be condensed, then it will be separated. And then we can take a sample, and then we can analyze actually the exhaust gases. Based on this method, we call it, this is the dry analysis. But does it mean, ya Shabab, if I have the dry analysis of the product, when I write down the combustion equation, should I just neglect H2O while writing down the combustion equation?
No,
No, we cannot neglect H2O. It was there in the combustion product, but I have condensed it. When I write down the combustion equation, it has to be balanced based on the law of mass action. And we should have H2O in this case. So if the dry analysis are given, in this case, I have to add also H2O in this case. Wet analysis, that means the analysis including actually the water vapor in this case. Okay. طيب here, Shabab, is an example. Is there delay, Shabab, in a slide? Which slide number does it show right now in your laptop?
34.
34.
34. So there is a slight delay right now, or it is going fine?
No, it's good.
طيب, that's fine. طيب, we have here شباب octane fuel is burned with dry air in a petrol engine. Octane is used actually in gasoline engine, and we have the dry volumetric analysis of the product are given actually as you can see here, and we need to determine actually the air to fuel ratio and the percentage of excess air in this case. So here شباب is the dry analysis. Dry analysis, that mean actually we don't have H2O. But does it mean H2O does not exist? No. H2O should be there in the combustion equation in this case. So in this case, I will assume 100 kilomole of the dry product. So if we have 100 kilomole of this product, I will start the combustion equation from the product side. 100 kilomole of the combustion product, so that means we have 10.02 kilomole of carbon dioxide plus 0.88 of carbon monoxide. In this case, I assume the 100 kilomole, not 1 kilomole. Okay, so 100, I will be just taking the number here. I will not divide by 100. And then I can write down the combustion product, plus 83.48 N2. In this case, I have to add what, I have to add H2O. There is an amount of H2O that has been actually condensated before doing actually this dry analysis. So we have to add here plus an unknown number of component, number of moles actually of H2O in this case. If we have 100 kilomole of this product, the fuel burned is octane, which is C8H18. We don't know actually the amount of fuel that can be burned in order to produce 100 kilomole of the product. So I will be assuming actually that we have a kilomole of the octane. Plus, I don't know also the value of the amount of air required actually in order to convert this a kilomole of the fuel in order to get actually 100 kilomole of the combustion product. So I will assume I have B number of moles actually of air in this case. Then we have in this case, in this equation, we have the three unknowns. We have A, we have B, and we have the number of mole of water vapor, which is C in this case. And then writing down the balance for N2, so it will be B multiplied by 3.76. That should equal to actually 83.48. And based on that, we can calculate the value of the constant B. It will equal to 22.2. Like this, we can make balance for carbon. We can get the constant A, which will equal to the number of kilomoles of fuel, 1.36. And we can make actually hydrogen balance to get the constant C, which is the number of kilomoles actually of water vapor in this case. It will be 12.24. I prefer doing this in your calculation to double check with the fourth element. We have O2, we can make O2 balance, then we can double check the value of B. B will equal to the same value that I have calculated, then actually my solution is correct in this case. Then we have the whole combustion equation is presented actually this way. To calculate the air to fuel ratio, should will equal to the number of moles of air, 22.2, multiplied by 32 plus 3.76 multiplied by 28. This is the mass of air. Mass of fuel will equal to the number of moles. In this case, the number of moles does not equal to 1. It is equal to A in this case. Okay, so it will equal to 1.36 multiplied by the molecular weight of the fuel, and we can calculate the air to fuel ratio actual in this case. Okay, how we can calculate lambda, How we can calculate lambda? Lambda is the air to fuel ratio actual, which is a value that we have just calculated, divided by air to fuel theoretical. To calculate air to fuel theoretical, I can write down the theoretical combustion equation for octane, which is C8H18, plus gamma, which is X plus Y over 4. X is 8 plus Y over 4. So it will be actually 4.5. So the total actually gamma will equal to 12.5. O2 plus 3.76 N2. Then the stoichiometric or theoretical air to fuel ratio will equal to 12.5 multiplied by 32 plus 3.76 by 28. divided by 1 multiplied by the molecular weight of the fuel. That should be the theoretical value. And we have the actual value, air to fuel ratio actual. If we divide both of them, then we can get actually the excess air factor in this case. The excess air factor will equal to 1.3. That means we have 30% excess air. Or it is actually what, ya shabab? It is equal to 130% theoretical air. So if lambda is equal to 1.3, that means we have 30% 0.3 excess air, 30%. Or we have actually, we can say we have 100, multiply lambda by just 100. That should give us actually the percentage of the theoretical air, which is 130% theoretical air. طيب, is there another way, شباب, to calculate lambda instead of calculating air to fuel ratio theoretical? So Ahmed Al-Khalaf, Ahmed, is there another way to calculate lambda? So we have written down here back the theoretical combustion for octane to calculate air to fuel theoretical. Then we divide air to fuel actual by air to fuel theoretical to calculate lambda. Is there another way based on this combustion equation to calculate lambda without writing actually the theoretical equation? Is there a way, Shabab?
Yes.
So Mustafa, go ahead.
We should divide the stoichiometric by 22.2.
Divide by 22.2 or divide by 1.36?
First divide by 1.36. Then we will get the stoichiometric times the lambda.
Exactly. So Shabab, usually we write down the combustion equation per 1 kilomole of the fuel. In this case, we don't have 1 kilomole, we have 1.36. So if I divided the whole combustion equation, all terms in the reactant and the product, by 1.36, so in this case, we will have the number of kilomoles of fuel will be 1. And the number of kilomoles of air will be 22.2 divided by 1.36. If we have the equation is written per 1 kilomole of the fuel, so the term here of air should equal to lambda multiplied by gamma. Gamma for this fuel, which is m plus m over 4, should equal to 12.5. So it will be 22.1 divided 1.36 should equal to lambda multiplied by gamma. And in this case, we can just calculate lambda. Otherwise, you can just write down the theoretical combustion equation for octane. Theoretically, Shabab, that means at lambda equal to 1. So it will be just the gamma of the air. Then we can calculate air to fuel ratio theoretical. And then we can divide air to fuel actual divided by air to fuel theoretical. Then we can calculate the value of lambda in this case. If this, Shabab, the concentration here are given actually on volumetric basis. And based on that, we assume actually we have 100 kilomole of the product. If the concentration are given by mass, it will be the same, but I will be assuming instead of 100 kilomole, I will be assuming 100 kilogram. So in this case, if we have 100 kilogram of this fuel, that means we have 10.02 kilogram of carbon dioxide plus 5.62 kilogram of O2 plus the other component. But when I write down the combustion equation, I need the number of moles. I don't need the mass. So in this case, I will divide for each actually element in the product. I will divide the mass of this element divided by the molecular weight. Then I can get the number of moles here. Unlike this actually for CO, for O2, and for N2. And for H2O, Shabab, there is no need to just divide by 18. This is a constant. So I will just 18, when you divide by the molecular weight, it will be also a constant. So just to say we have a constant of H2O. Okay. So divide the mass by the molecular weight, we will get the number of moles, plus we add CH2O, and here we assume we have A plus B. And the same way you will be solving actually for A, B, and C. Then you can calculate the air to fuel ratio. And also you can calculate the excess lambda is the excess air factor. We can calculate also the lambda value. Is that clear, ya Shabab? Is it clear?
Yes.
So شباب يعني now we have learned how to write down the combustion equation if we have single hydrocarbon, mixture of hydrocarbons, if we have as well actually alcohol fuel, if we have hydrocarbon with alcohol fuel, if we have the product analysis, the fuel analysis like coal or something or natural gas, which have a lot of components, how to write down the combustion equation. And also if we have the product analysis, also we have learned how we can calculate the excess air ratio lambda and how we can calculate the air to fuel ratio in this case. طيب here is an example يا شباب. I will يعني end up with this example. As I told you, Shabab, we have taken a chapter on the fuel families. So here I'm writing here actually the chemical structure of the fuel. I said we have decane fuel, but when I tell you we have a decane fuel, you have to realize actually that this is the alkanes family, which has the chemical structure CnH2n plus 2, and the dec, which is the prefix, indicate actually the number of carbon atoms is 10. So CnH2n plus 2, that means the number of hydrogen atoms should be 22. So when I say decane, that you have to realize actually that this is C10H22, okay? Without writing, I will not write it, okay? This is burning with 95% theoretical air. So lambda in this case, شباب, is equal to what?
0.95.
Exactly. So lambda in this case is 0.95. So when I say theoretical air, I have to divide by 100 in this case. So let's say 95. So that means lambda is equal to 0.95. That means يا شباب what? That we have less air or excess air?
Have less air.
We have less air in this case. But if we have less air, that means actually we will not have some O2 in the combustion product. O2 is not even enough in this case. And the combustion in this case, Shabab, will be what? Complete or incomplete? Incomplete combustion. So in this case, we should have all carbon should be converted to carbon dioxide. But actually, we don't have enough oxygen. So some carbon monoxide will appear actually in the combustion product. And this is what he said. He said the combustion product contains the carbon dioxide, carbon monoxide, plus water vapor, plus N2 in this case. Those are the combustion product. طيب why يا شباب؟ يعني we have carbon and hydrogen and they compete actually for oxygen. Usually actually when carbon and the hydrogen compete for oxygen, usually hydrogen actually will win this game. Because hydrogen is highly reactive, has very low viscosity, it can diffuse faster, so it can mix actually with oxygen faster, so it will be approaching oxygen faster in this case. So if lambda is less than 1, usually hydrogen most probably will not be in the product. But actually the components that will be in the product will be what? Will be the carbon monoxide. Okay, and this is one of the main emission. Carbon monoxide is a very toxic gas. It does not have a color or does not smell as well. So it's a very dangerous actually exhaust product. So here in this case, Shabab, I will just write down the combustion equation the regular way. We need to calculate the air to fuel ratio first of all, and we need to analyze. We get the dry and wet analysis of the product. Okay. So let's write down the combustion equation. 1 kilomole of this fuel decane plus lambda, which is 0.95, by gamma, which is 10 plus 22 over 4, m plus n over 4, O2 plus 3.76 N2. In this case, Shabab, I cannot say we have MCO2, 10 CO2. We don't know because it's incomplete combustion. We have CO2 plus CO. So I will assume we have alpha parameter, alpha number of moles of CO2, plus beta of CO, plus N2 in this case. It will be gamma N2, but yani N2 is an inert gas. Yani you can write it down here. It will, gamma will equal to 0.95 multiplied by 15.5 multiplied by 3.6. Here it is. So this is gamma. It will be 55.36 plus delta H2O. Okay. And then we can just make balance alpha, beta, and gamma, and delta. will be calculated from the balance of carbon, hydrogen, nitrogen, and oxygen. Then we can get actually the 4 parameters in this case. And then we can write down the combustion equation. So if lambda shabab is less than 1, that means we should have some carbon monoxide in the product. And in this case, we can write the combustion product in terms of unknown. And in this case, we can just make the balance to calculate actually all of these unknowns in this case. And we can calculate the air to fuel ratio. It will equal to lambda by gamma, which is 0.95 multiplied by 15.5 will equal to 14.72. 5 multiplied by the molecular weight of the air divided by, as we used to do, the number of mole of the fuel multiplied by the molecular weight of the fuel. Then we can calculate the air to fuel ratio in this case. But we need to have the dry and wet analysis of the combustion product as well. So in this case, I will look at the combustion product. We have 8.45 CO2 plus 1.55 kilomole of CO plus this number of kilomoles of N2 plus H2O. In case of dry analysis, shabab, I will just actually neglect H2O as if actually it does not exist. So in this case, for the dry analysis, this is the combustion product, CO2, we have CO, we have N2, and H2O in this case is just a condensate. So we have, this is the number of moles of those components. Based on the combustion equation, we have calculated those number of moles. We have the molecular weight for each component. Then we can calculate the mass of each component. Mass will equal to the molecular weight multiplied by the number of moles. Then we can calculate the mass of each component. If we sum up all masses for all components, then we can calculate the total mass. Like this, we can calculate the total number of mole of the product, but neglecting, for the dry analysis, neglecting H2O. So we have in this case, the total number of mole will equal to 8.45 plus 1.55 plus 55.366. This will be actually the total number of mole. And to calculate the mole fraction, based on the dry analysis, will equal to the number of moles for each component divided actually by the total number of moles. The mass fraction for each component will equal to the mass of each component divided actually by the total mass. Then we can get actually the dry product analysis based on mass fraction, based on mass basis, Xi, and also based on the volumetric analysis based on actually the mole fraction, which is Yi in this case. Is that clear, Shabab? Is it clear?
Yes.
This is the dry analysis, Shabab. Is something I think you are aware about that. In case of wet analysis, I will be just considering all of the product, including actually H2O in this case. So for the wet analysis, I will add H2O, and the same way I will calculate the number of moles, total number of moles for the product. Then we can calculate the mole fraction, which is the number of moles for each component divided by the total number of mole. I can get actually the wet analysis based on the volumetric analysis. For the mass, we can get the mass for each component. Mass will equal to the molecular weight multiplied by the number of moles for each component. Do it for all components. Then we can calculate the total mass in this case. Okay. Then we can calculate the mass fraction, which is the mass for each component divided by the total mass. We can get actually the mass fraction in this case. The summation, Shabab, you can just double check. The summation of all mole fraction and mass fraction should sum up actually to a value equal to 1 in this case. And those are actually the dry analysis and the wet analysis of the combustion product. You can try this example, Shabab. There are too many examples today, so you can just even try this example. Do you have any question regarding this chapter, Shabab? So is there any comment? Do you need something just we can go back and try to revise it? Shabab?
Doctor?
Yes.
Just a conceptual question maybe. What's the benefit of doing the dry and wet analysis?
Sorry?
Why do we do dry and wet analysis? Why don't we do just one of them?
Just what? Why you don't do just what?
We do dry analysis and wet analysis, right?
Yes.
What's the benefit of doing both?
What is the benefit of doing both of them? We can do one of them only?
Yes, that's the actually.
Yeah, for the dry analysis, as I told you, it's related actually to the design of the gas analyzer. So if the gas analyzer itself is designed actually for dry analysis, that means actually we have to condensate water vapor in the exhaust gases, cool them down in a cooling system before we take the sample in order to analyze. Because the gas analyzer itself will be sensitive to H2O. So it will result actually in incorrect result or bad result in the analysis in this case. But if the gas analyzer is already designed to account for the wet analysis, to account for H2O, then in this case actually we have to consider we can get the full analysis. So it depends on the design of the gas analyzer. Okay, most of gas analyzers, they just actually consider actually the cold sample. They sample actually take a sample of the exhaust gases, cool the sample, cool the down sample at a low temperature, so that actually the water vapor is condensed. We don't have water vapor. Then it can actually, they can give you the analysis of the combustion product in this case. Usually, there is a special kind of sensor to measure the concentration for each component, and each actually sensor has a separate technology. Either actually infrared sensor or ultraviolet or something. So there are different methods actually used in the analysis of the combustion product for each species. They have to make a test in order to calculate the concentration for each species. Okay, so usually they prefer also not to add H2O because we can just condense it, and at the end actually the summation of all of the components should sum up to 1. So if I just neglect H2O, which will make a problem, and we need to add additional sensor in order to measure it. So in this case, we can just condensate it, and after calculating the mass fraction of all species, we can consider the equation like what we have considered, and we can get the value of the number of H2O molecules actually in the product as well. So we don't need actually to consider it. And that's why you will find most of gas analyzers, they are based on the dry analysis. They don't consider actually H2O. Okay.